So we're going to review now for our test at the end of this week. And basically it's the BCA stuff. We've got gram amounts of reactants. We need to write their formulas based on what type of compound they are, predict the products based on what type of reaction it is, balance the whole thing, convert those grams into moles, do the BCA calculations, convert them back into grams, and then compare them with the actual amount produced to find a percent yield. And so it's a pretty long, involved process, but we'll get started here. The steps are written out for what you need to do here on the review. We're going to start by writing the complete balanced equation. And for number one, it's 254 grams of copper and 160 grams of sulfur. So our equation is copper and sulfur. We're going to note that we have two non-ionic reactants. So this is a combination or a synthesis. All we can do is put copper and sulfur together. And it says it's copper 1, so it's plus 1 and minus 2 for the sulfur. So it ends up being Cu2S. We've got to balance the whole thing. Got two coppers. Make sure we have a 2 there. One sulfur, and that's all done. So we're 2, 1, and 1. And, the next step is to convert the grams into moles because we have 254 grams of copper and 160 grams of sulfur, and we can't use grams, so we're going to take the 254 grams of copper divided by the molar mass, 63.54, and that turns out to be right at 4 moles of copper. So we can go ahead and put that number into our BCA table. We also have to convert the 160 grams of sulfur at 32.06 grams per mole, and we end up with 5 moles of sulfur. Go ahead and put that in there. We know that we don't have any product to start with. And we need to identify the limiting reagent because we can use the 4 moles of copper to determine how much copper 2 sulfide, 4 divided by 2 times 1 is 2, or the sulfur, 5 divided by 1 times 5 is 5. They both give us a different answer. We need to find which one of these is going to run out. And we do that just by comparing. We know that for every 2 coppers, we only need 1 sulfur, so we always need half as much. Or we can do it systematically. 4 divided by 2 is 2, times 1 is 2. So if we have 4 of these, we need 2 sulfurs. That tells us that sulfur is in excess. We have plenty. And copper is the limiting reagent. Okay, so this is our limiting reagent, and this is the important number to use. So we're going to use up all of the copper to be left with none. And now we're going to use this number to determine all the other amounts in the BCA table. 4 divided by 2 is 2, times 1 is, we're going to use up only 2 sulfurs and be left with 3 after the reaction. Still using the limiting reagents number, 4 divided by 2 is 2, times 1 is, we're going to make 2 copper 1 sulfides. So at the end of the reaction, all the copper will be gone. We'll have 3 moles or particles of sulfur and 2 copper 1 sulfides. So we're going to draw our picture here. I'm going to draw the coppers as red, and we have 4 of them. And I'll draw the sulfurs as green, and we have 5 of those. And we're going to make as many copper 1 sulfide, Cu2S's, as we can. So each one has 2 coppers and a single sulfur. That takes care of 2 coppers and a sulfur. I'll make another one. 2 coppers and a sulfur. That takes care of that. I can't make any more. I've run out of copper. So what I have left, though, is I still have 3 sulfurs. So these should, the after of the BCA table and the after for the picture should say the same thing. I don't have any just copper atoms freely running about. And I have 3 sulfurs left over and 2 copper 1 sulfides. Now that's all that is left for me to do is do the final percent yield calculation. I'm going to take my 2 moles of copper 1 sulfide, Cu2S, and I'm going to convert it into grams by multiplying by the molar mass of copper 1 sulfide. So the weight of 2 coppers and 1 sulfide is 159 grams per mole. When I do that, I get 318.3 grams. But it says, this is what I should have produced, 318.3 grams, but I only produced 291. So we're going to find the percent yield. We're going to grade this reaction, multiply it by 100 to make it a percent, and this turns out to be a 91.4% efficient reaction. I'll move on and I'll do one more. I'll do number 3. It's an interesting one to do. The numbers are a little different, but what you do is the same. Okay, this one is 623.4 grams of iron 3 sulfide reacts with 72.9 grams of magnesium metal. So we'll go ahead and write the complete balanced reaction as iron 3 sulfide. That's an ionic compound, so we're going to say symbols, charges, cross them, so it ends up Fe2S3 is mixed with magnesium. And it says I have, its formula is just Mg. I have 623.4 grams of that and 72.9 grams of that. Okay, this is 2 reactants. One of them is ionic, so this is a single replacement. This single lone metal is going to come over and replace the other metal, the iron, and kick it out of place. So we're now going to have magnesium bound to the sulfur, +2 and -2. They'll cross and cancel. And the iron over here by itself. And now we have to balance. I have 2 irons on the left, so I have to have 2 on the right. 3 sulfurs on the left, so I have to have 3 of those on the right. That gives me 3 magnesiums. So I'm balanced at 1, 3, 3, and 2. Now, I can't use these gram amounts. I've got to go ahead and convert those grams to moles. So 623.4 grams of Fe2S3 divided by the molar mass of iron 3 sulfide, which is 207.8. Remember, that's the weight of 2 irons and 3 sulfurs. That gives me 3 moles of Fe2S3. So we'll go ahead and populate that part of the BCA table. And then we'll convert the 72.9 grams of magnesium by dividing it by its molar mass. And we'll also get 3 moles. Okay? So we'll go ahead and put that in there. We know that we have no products to begin with. And now, this is a pretty easy one to decide which is the limiting reactant. We have 3 moles of each. By count, we have 3, for every 3 iron 1 sulfide, or iron 3 sulfides, we have 3 magnesiums. But we know in the reaction that we need 3 times as much magnesium. So we don't have enough magnesium, so this is our limiting reagent, and that means that is the important number. We're going to use this 3 to solve for all other amounts in the BCA table. We're going to use all 3 moles of the magnesium to be left with nothing. 3 divided by 3 is 1, times 1 is we're only going to use 1 mole of the iron 3 sulfide to be left with 2. And as far as the products, we're still going to use the limiting reagents number. 3 divided by 3 is 1, times 3 is 3. 3 divided by 3 is 1, times 2 is 2. So we should, in the end, in our picture, we know that we're going to end up with still 2 moles of iron 3 sulfide, all of our magnesium by itself gone, 3 moles of magnesium sulfide, and 2 moles of iron will be left over. So I'm going to draw my magnesiums here. All 3 of them is purple circles. That'll be my magnesium. I'll make my iron the red circles and my sulfur the green circles. So I've got 3 Fe2S3. So just draw them however I want, just as long as I differentiate the different atoms. I'm going to make as many MgS's as I can, so the MgS's are going to be an Mg and an S, and I can certainly do that, and I can make another Mg and an S, which gets rid of another one. Another MgS gets rid of that. Well, I certainly have more sulfurs, but I don't have any more magnesium, so I can't make any more MgS's. But I have 2 of these iron 3 sulfides still untouched, unchanged. So that gets rid of those 2 things. And then I have 2 iron atoms floating off by themselves. And again, the after of the BCA table and the after the picture should say the same. I have 2 iron, I have 3 magnesium sulfides, and I still have, I have 2 irons, 3 magnesium sulfides, and I still have 2 of these iron 3 sulfides. All right, one last thing is to find the percent yield. I'm going to take this magnesium sulfide, the 3.0 moles of magnesium sulfide, and I'm going to multiply it by its molar mass, and it's 24.3 for magnesium, 32.06 for the sulfur, so it's 56.3 grams per mole. Tells me that I should have produced 168.9 grams of magnesium sulfide. Well, the problem tells me I only made 50, and again, we're going to grade the reaction. We're going to take how much we actually got divided by what we should have gotten, that the BCA table told us, times 100 to make a percent. In this case, it's a pretty low percent, 29.6% efficient reaction.